Hello, this is Lab 4, Stochastic Local Search for Comp 380. Question 1 asks, in local search, how do we determine neighbors? So determining neighbors depends on the size and ordering of the domain. So if the domain is small or unordered, we choose a neighbor by changing the value of one of the variables. While if the domain is large and are ordered, we choose we change the variable value to an adjacent one. So for example, in the first case, if we have three variables, A, B, and C, a neighbor would be changing the value of B to something else. And then in the second case, if we have, let's say, a numeric domain, if we have a variable that's equal to 4, a neighbor could be making that equal to 5. The difference between a random walk and a random restart is a random walk moves from a variable to a random neighboring variable, while a random reset assigns random values to all the variables. And then the two key weaknesses of stochastic local search are the fact that it's incomplete and suboptimal. Therefore, it is not guaranteed to find a solution if one exists, and if it does find a solution, it is not guaranteed to be the optimal solution. And then the next questions are related to this constraint satisfaction problem. 8 intersections. This one has to be a four-way. These cannot be roundabouts. Only one roundabout per square of 4. And there cannot be two of the same intersection consecutively. So if we run greedy descent on this sort of subsection of the problem, what will happen? Or what variable will be selected first and what value will we assign to it? So as stated above, we choose the variable under most constraint. So intersection 3 is under 0 constraints, as this one satisfied. Intersection 2 is under 1 constraint, as these two are the same. So C2 is not satisfied. And intersection 1 is under 2 constraints. It is both not a four-way stop under C1, and these two are the same consecutive. So we will choose intersection 1, and we will make it a four-way stop in order to satisfy both of these constraints. With the same partial CSP, so this one, how likely would it be to find a solution within 100 steps using only random walks? I think that we are quite likely to find a solution within 100 random walks due to the fact that this is a pretty small constraint satisfaction problem. There's only 3 nodes, and the domain of each node is only 3 values. So I think it's quite reasonable to assume that we will. It is not guaranteed, but reasonable to assume. And then part 5 is representing the problem in AI space and solving it. So this is the representation of the problem. You can see all the different constraints and nodes. So if we go into solve, and then we can do, so it says greedy descent, just random walks, and greedy descent with random walks. So we'll run greedy descent. We'll run greedy descent. So there you can see there's greedy descent, and then we will run random walk on sort of the same problem. There's a random walk, and then we will run greedy descent with random walk. There we go. Here, let's run. And there you can see the plot of all 3 of the algorithms. You can also see the statistics, right? So for plot 0, there's just greedy descent. You have a mean of 30 steps to solve it. For random walk, it's 100, right? So you have, it's much worse for one. And then for plot 2, it is 37 steps. So it's a little worse than plot 0 in this case. And you can also see the time each algorithm took. All right, that's it. Thank you.